Welcome to this video on eigenvalues and eigenvectors. First, I'll talk about what these actually are. Then I'll look at the theoretical approach to solving them. And then we'll look at a practical example of applying this solution approach to solving for the eigenvalues and eigenvectors. Okay, so what are eigenvalues and eigenvectors? You need to set the scene by understanding that we're looking at some sort of linear transformation of a matrix transforming a vector x. And if you think about matrix A as a n by n matrix and vector x as a n by 1 vector, then outside of the concepts of eigenvalues and eigenvectors, this would be a linear transformation applied to the vector x. And what eigenvectors are a specific application of a linear transformation where it's resistant to whatever this matrix of transformation is doing to the vector. So if this matrix is multiplied to this vector and the direction of that vector is maintained, it's just scaled up or down, then we have a special case of a linear transformation not really doing anything to the vector. And that is why we have an eigenvalue and eigenvector where the eigenvector multiplied by the linear transformation maintains its direction and then is scaled up or down by the eigenvalue. So let's look at an example. Let's look at an example of not an eigenvalue and eigenvector. If you had matrix A, which was equal to 1, 2, 3, and 4, and then you multiplied it by a vector x, which was just 1, 1, you're applying a linear transformation here to the vector 1, 1. And you could put in any vector in terms of x and multiply it by this linear transformation, and it will have a specific style of transformation that is being applied. And in this case, I just plugged it into a calculator. A multiplied by x is equal to, in my calculator here, we can get it into the light, is equal to 37. And what you notice about this transformation is that is definitely not in the direction of 1, 1. It's not 3, 3 or 7, 7. It's in a new direction that has changed it from 1, 1 into something like 3, 7. And yeah, that is a linear transformation that has been applied to x. But a special type of transformation is one where you multiply it through and it maintains that direction but just scales it up or down, etc., but keeps it in that direction. And that is the idea of an eigenvector and an eigenvalue that is resistant to the linear transformation. So that's essentially what this is saying here. A matrix times a vector maintains the direction of that original vector and is just scaled up or down by this constant. It's unaffected by the linear transformation. Okay, there's so many uses for eigenvalues and eigenvectors, too many to list. But in this video, we're just going to look at trying to work out what they actually are for a matrix A. So your focus is on the matrix A, if I can get the lighting, in this case 1, 2, 3, 4, and then working out what vectors being multiplied by this linear transformation will not get transformed essentially, or get transformed in a specific way that's just a scalar multiple of it. So to work out what that is, this is what we do. We know that what we're looking for is A multiplied by x is equal to lambda x. We just don't know what x and lambda are. But that is logically equivalent here to A multiplied by x equal to lambda multiplied by I times x. And then if we subtract lambda I x from both sides, we have ax minus lambda I x equal to 0. And then we have a minus lambda I x equal to 0. And then here, this is only going to be equal to 0 if the determinant of a minus lambda I is equal to 0. So essentially we solve for the eigenvalues and eigenvectors by finding when the determinant of this is equal to 0, what lambda will make this determinant equal to 0. Now, the reason why this is true is related to other concepts of linear algebra, which I'll touch on in another video, but this is logically equivalent, that is only equal to 0 if this is equal to 0, the determinant. So the last step is a result of bx equal to 0 and b not equal to 0, then x equal to 0 is the only solution. So we're utilizing this fact by finding when the determinant is 0 to have the solutions that we're looking for. Okay, so practically what we do, if we're given a matrix A and we're asked to find the eigenvalues and eigenvectors of that matrix, we first construct A minus lambda I as a matrix, and then we derive the determinant of that, and then we solve the polynomial equation of setting this determinant equal to 0, and that will usually be in terms of lambda. Finding the corresponding eigenvectors can be a little bit harder, but you construct at step 3, you will have found your eigenvalues from doing this. And once you have your eigenvalues, then you find your eigenvectors by doing these following steps 4 and 5. So you can construct your A minus lambda I for a specific lambda that you've worked out, and then you can solve for all of the vectors that give you 0 using Gaussian elimination. Okay, and then just a note for down here, the eigenvalues are not unique to the the eigenvectors are not unique to the eigenvalue, rather they're in a direction and can be scaled up or down accordingly. So if you get 2, 3 as an eigenvector for lambda equals to 3, then 4, 6 will also be an eigenvector for lambda equal to 3 because it's in the same direction. And so we have a set of eigenvectors that are all vectors in the direction, in this case 2, 3. And alpha, if it's a real number multiplied by that, will give us our eigenvectors. All right, let's take a look at an example now. Okay, so for our example, find the eigenvalues and eigenvectors of A equal to -5, 2, 2, -2. So we're going to follow that same approach as before, where we construct our A minus lambda I matrix. Lambda I is just lambda multiplied by the identity matrix, which is this, So when we have A minus lambda I, what we're really doing is just subtracting lambda from the diagonal here. Okay, the determinant of that is the diagonals multiplied by each other and the difference of those two things. So we have the diagonals multiplied by each other here minus this. And then once we expand that out and we simplify things down, we get left with a polynomial equation in terms of lambda. And factorizing that, we get lambda plus 6 multiplied by lambda plus 1. And what we're looking for is when this determinant is equal to 0. And so now we know that lambda is equal to -6 or lambda is equal to -1 using our null factor law to determine what these eigenvalues are. Okay, and now that we know what the eigenvalues are, we want to find the eigenvectors that correspond to these values. So first, let's start with lambda equals to -6. And if we plug that into our A minus lambda I, we're adding 6 to these diagonals here. So -5 plus 6 is 1, -2 plus 6 is 4. And now we want to find the vectors where A minus lambda I multiplied by the vector will give us 0. So we have a augmented matrix here, 1, 2, 2, 4 equal multiplied by x equal to 0, 0. And we're looking for the x that will give us this. And using our Gaussian elimination techniques, this second row is completely eliminated by subtracting 2 multiplied by the first row. And that means that we have x1 plus 2x2 is equal to 0. And so x1 is equal to -2x2. And any vector of this form will satisfy this and will hence be an eigenvector for this eigenvalue. And so the set of eigenvectors is then categorized by this here. Alpha is a real number multiplied by -2 and 1, and that will scale things up or down depending on what alpha you pick, but maintaining that direction here, matching for this eigenvalue. And then we do it again, but this time we're looking at the second eigenvalue and finding the corresponding eigenvectors for that. And it's the same approach. You have -4, 2, 2, -1 because we've added 1 to those previous diagonals. And then doing our Gaussian elimination, a whole row gets eliminated into just zeros, which frees up these variables to be 2x1 minus x2 equal to 0. And so any vector that satisfies this will be an eigenvector corresponding to this eigenvalue. And so we can categorize it as this set of vectors here, as so. Okay, just in reflection, something that you'll notice when you're looking at eigenvalues and eigenvectors is that by the time you've worked out the eigenvalue and then have a minus lambda I here, you should have linear dependence upon the rows, so that when you get to the augmented matrix here, one row will become 0, 0, 0. And in fact, we've actually used our linear algebra invertibility theorems, which will be covered in another video, to exploit the fact that this determinant is 0, which means that the rows are not linearly independent, so they're linearly dependent, which will get us into this form. So that is why you'll always have the case when you're solving this augmented matrix that you have a bunch of zeros here, because we have set it up for the reason of having the linear dependence in the rows here. So that is just 2 times the first row, and this one here is -2 times the second row, linear dependence. All right, so that's how you work out the eigenvalues and eigenvectors. Make sure you always find the set of vectors, not just one example vector. And also, if you have a higher dimension matrix A, you will have potentially more eigenvalues and eigenvectors as well. All right, thanks for watching this video.